On July 1st, 2025, as the world welcomed the third confirmed interstellar visitor, Tri-AI Atlas, Chinese observatories published a stunning new image showcasing unprecedented details. At the same time, leading Western telescopes unexpectedly ceased operations. Some astronomers believe these shutdowns seriously affect Earth's response speed to cosmic threats, especially when unique data streams may elude us. Amid rumors of strange rotations and unusual trajectories, the story of Tri-AI Atlas quickly becomes more than just a race for discoveries. This is a test of global cooperation, data transparency, and even planetary protection. What can these recently discovered images tell us about our mysterious guest? And why has their publication sparked such a storm of debate among scholars and the public? The official bulletin announcing the opening of Tri-AI Atlas was released on international networks on July 1st, 2025. A group of Atlas researchers in Hawaii and Chile recorded a faint, fast-moving object on an unusual trajectory. For several hours, the hyperbolic trajectory of the object and its arrival speed confirmed what astronomers had quietly hoped for. This was only the third interstellar visitor ever observed passing through our solar system. Designation 3-2, the third interstellar object, appeared in the database of the Small Planet Center before sunrise in Europe. By noon, astronomical forums were already buzzing with speculation. People began to ask the same questions as about Oumuamua and Boris. Where did it come from? What is it made of? But this time, the rumors spread even faster. Social networks picked up information that Tri-AI Atlas was exhibiting strange spinning, possibly even tumbling motion, and that its trajectory through the solar system did not match predictions. Astronomy enthusiasts began comparing early brightness curves with those of previous visitors, trying to find patterns or something unusual. The novelty of the discovery and the fact that only two similar objects had been confirmed until that moment added a sense of urgency. For astronomers, such events are not just rare, they define their careers. The last time this happened was in 2019 with Boris. Before that, in 2017, when the strange cigar-shaped object Oumuamua sparked debates that still continue. Now, in the year 2025, the world was once again watching the cosmic messenger, and time was running out. The initial notification of the Atlas team included key parameters: an entry speed of over 60 kilometers per second, predicted maximum approaches at sunset at the end of October, and a preliminary core size estimate, determining the core diameter to be about 30 to 50 kilometers, significantly larger than Oumuamua, with a noticeable coma. This last detail sparked a wave of interest. Unlike dry comets like Oumuamua or the icy Borisov comet, Tri-AI and Atlas represent something intermediate. With each moment, as news spread, the value of each new observation became increasingly evident. Forums were filled with messages about the operating times of telescopes, data exchange, and logistics for capturing a fast-moving object before it disappeared from sight. However, in the background, other conversations arose. Rumors began to circulate that several major Western observatories were planning maintenance or upgrades. Triad and Atlas came into the main visibility range. Some considered it an unfortunate coincidence, while others wondered if the timing was something more than just bad luck. At that moment, it was clear that the discovery of Triad and Atlas had become more than just a scientific note. It was a world-scale event, and every rumor, every piece of data, every missed observation window fueled a story that became increasingly grand and unpredictable with each passing hour. Every hour after the opening related to Triad and Atlas, the scientific window for an object racing through the solar system at over 60 kilometers per second is measured in days, and sometimes only hours. That is why astronomers strive to gather as much high-frequency data as possible. Quick snapshots and spectra allow tracking every flicker, every gas burst, every barely noticeable change in brightness. For Tri-AI and Atlas, the reward for collecting this data goes far beyond a few good shots. High-frequency photometry allows for recording the brightness curve of a comet at short intervals, sometimes every 15 minutes or even faster. Thus, scientists notice control dips and peaks that indicate the rotation speed or irregular motion. In the early rumors about the core with an active crust, these measurements became even more relevant. If the object rotates chaotically or its surface consists of alternating bright and dark materials, such patterns will be the first to appear in the brightness curve. For Trion and Atlas, some astronomers suggested a rotation period of more than 12 hours with possible evidence of complex rotation, different from the main axis. Such movement may indicate recent collisions, a distinct structure, or even a binary core, each having its implications for how the object formed and what forces shaped it as it drifted between the stars. But it's not just about the rotation speed of Tri-A and Atlas. Rapid spectroscopy, splitting the light of a comet into its chemical components, can reveal jets of carbon, water vapor, or more exotic molecules erupting from its surface. These fleeting emissions have short-term value, as they can flare up and vanish in less than an hour when sunlight hits fresh patches of ice. With each missed observation, the chances of capturing one of these events decrease. If the jet accidentally changes its direction, it can slightly alter the comet's trajectory by a minor but measurable amount. This is a real-time physical experiment happening millions of kilometers from Earth. Thus, scientists explain the non-gravitational acceleration that can be observed in Muamma, Boris, and now possibly in 3 pairs of eyed plasmas. This urgency has not only academic significance. Each new interstellar visitor is a unique opportunity, occurring once in a generation, to test models of planet and comet formation around other stars. If Tri-I Atlas truly exhibits a combination of cometary or singular features, or if its coma is formed by streams unlike anything observed before, the data collected in the first hours could change textbooks. Some theorists have even proposed the hypothesis that such transitional objects may be the missing link between comets and long-period comets. This idea can only be tested with high-frequency data across several long wavelengths. Therefore, when astronomers talk about bets, they mean this: several nights, uncertainty of data, and the possibility of answering questions that have remained unresolved since the discovery of the first interstellar object. If the necessary evidence is obtained, such as curved rotations, unstable signatures, or trajectory shifts, it could change our understanding of the structure of other solar systems. And if this window closes, the chance will be lost. The engineering journals of Observatory K and K for the semester of 2025 look like a checklist of missed opportunities. DEIMAS, the main tool for spectroscopy and studying faint objects, was shut down from the end of May until the end of the semester for detector upgrades. NIRSPIOC, a near-infrared spectrograph, went into sleep mode for 5 weeks starting May 6th. By the time TREA and OLAS entered the operational zone, most of the powerful K and K instruments were unavailable. Even the adaptive optics system on the K and K faced shutter failures, increasing downtime for both imaging and spectroscopy. These were not just scheduled breaks. They occurred precisely when astronomers needed to observe the sky by all available means. Twilight observation programs continued, cramming in all possible observations, but the rhythm was disrupted. Home observations of the remote reserve, which supported science during the pandemic years, were still operational, but only for tools that had not been preserved. Astronomers working in the temporal domain, relying on target capability adjustments to capture rare events, found that their capabilities for the Tri-I Atlas had significantly diminished, meaning the chances of obtaining high-resolution spectra or rapid photometry had simply vanished. Official notices about the schedule and status of instruments confirm what is happening. The lack of data and adjustments led to a series of missed nights. The Gemini observatory, located between Hawaii and Chile, faced its own challenges. The cyber attack that paralyzed both facilities in August 2023 had become old news. However, problems in Tertia continued into the following year. Software updates aimed at enhancing security ultimately blocked access to the multi-object spectrograph just as the interstellar object became brighter. Internal emails from the Gemini team indicate a hurried attempt to relocate research. But, as noted by one astronomer, the observation window has been missed. The object has already surpassed the optimal threshold of stellar magnitude. Log records show a slowdown in response. Requests for operational actions were rejected, and some were never completed. Tool wait modes, failures, and software conflicts are part of the life cycle of any observatory. But the combination of these problems for Kai and Gemini during the critical days of the Tri-A passage was not just bad luck. The registration logs, notifications of schedule changes, and engineering reports indicate a certain pattern. The gap in the data was real and documented in black and white. For astronomers, every missed night is a gap in the brightness curve, a void in the spectrum, a lost opportunity to capture a cosmic emission before it disappears. Engineers and technical staff from both observatories spent these weeks dealing with problems, balancing maintenance with urgent requests from desperate scientific teams. Some decisions were made too late, while others, like updating the adaptive optics in Kiev, simply could not be rushed. As the observation window narrowed, reality made itself known. The world's largest telescopes, designed to register the rarest events, took a back seat due to their complexity. The remaining gaps define the entire story of Tri-AA. Official statements began to arrive almost as quickly as the notifications of outages. The National Science Foundation described Gemini's downtime simply as a series of updates and shutdown protocols. The European Southern Observatory pointed to a sudden instability in the power grid, stating that the outage was beyond their control. When NASA was asked about the missing images from the Mars Reconnaissance Orbiter, they referred to ongoing government shutdowns and delays in processing the images. But even with all the documents and public explanations, time caused concern for many astronomers. 3 world-class observatories, each operating on its own schedule, lost access to the same critical window. Statistically impossible, yet it happened. Several technical specialists made statements about this. The class of outages was described as extremely unusual. Some experts pointed out vulnerabilities in the schedule and infrastructure that rarely manifest simultaneously unless something large-scale occurs, such as a mass software update or network failure. Others, especially those who have worked with these objects, disagreed. They claimed it was just the price to pay for the work of complex machines under tight budgets and deadlines. Service windows overlap, equipment fails, and sometimes the universe simply doesn't care about your observation schedule. The discussion sparked a heated debate in the astronomical community. On one side, voices claimed it was a perfect storm of failures. On the other hand, some began to analyze the numbers, trying to calculate the probability that 3 major observatories would shut down simultaneously during once-in-a-decade events. The figures turned out to be uncertain, with too many moving parts and unknowns, but the feeling of disappointment was real. Missing the chance to see an interstellar guest was not just a lost night. For some, it could be the end of a research project. For others, a fleeting opportunity of great importance in their careers. An official statement about delays with the camera on the skyscraper was of no help. Due to the prolonged shutdown of the United States government, image processing and publication were halted. This created a gap in the data flow that no one could fill. Not even the best amateur setups. Astronomers relying on these images for quick analysis, tracking jets, rotations, or flares were forced to wait, updating data streams and hoping for luck. All of this fueled speculation both online and offline. Some wondered if there were deeper reasons for the mass outages, security protocols, data integrity checks, or even excessive caution in the face of an unexpected discovery. Others believed it was merely a routine failure, exacerbated by a rare case of a cosmic visitor. Regardless, the outcome remained the same: a gap in world history, and a story now reliant on available data. File headers and dataset identifiers told their story. Large public archives, whether a small planet center, a mast of the National Security Agency, or the data portal of the European Southern Observatory, contained a list of 3 observations, clearly structured. All raw files from the first detection to subsequent shots come from the Western Observatory. Dates, instrument settings, and observer data were recorded in each file. There were no signs of involvement from Chinese organizations. There are no identifiers for datasets with Chinese names or links to Chinese sites. Searching Chinese platforms and official channels yielded nothing related to data publication. International repositories also contain no Chinese data or links to datasets. Instead, each timestamp and exposure note points to Atlas, VLT, Gemini, Hubble, and TSS, even when searching the metadata with cross-references. Western sources provide complete logs and release notes. The notifications about discoveries, published through the agency and the observatory, indicate that the review is marked as the initiator. There are no gaps, missing data, or unexplained delays related to the Chinese observatory. Direct verification with institutional press services and inquiries into databases confirm this pattern. No Chinese observatory has published images, spectra, or accompanying files for the three-eyed since October 25, 2020, and the origin of the data remains pure. All available images and datasets are obtained from Western sources with corresponding metadata. If new data emerges, it should be published through official Chinese channels. But nothing is known about this at the moment. The statement about the Chinese release is simply not supported by evidence in any known archive. Photos taken by Chinese observatories during the power outage added a new level of detail to the tiny tree atlas. The coma, usually a blurry round cloud for most comets, showed a pronounced extension in the shape of a droplet, almost like a wind cone trailing behind the object. Some astronomers suggest that this may be the result of solar heating, causing the release of carbon dioxide and sulfur carbon, which were strong in spectral analysis. One of the samples also contained ice, although its composition did not quite match what was observed in Boris or Oumuamua. Instead, he hinted at a mixture, partially cometary, partially icy, possibly even representing a transition between two types of interstellar objects that we had cataloged so far. The observational data added another mystery. The curve of brightness suggested a core about 46 kilometers in diameter with a possible rotation period exceeding 12 hours. Some speculate that the object may not even be a tightly bound double, or at least have a surface with highly varying reflective capabilities. The way the comet flared and shifted in just a few hours indicates active jets, possibly even sudden outbursts, as sunlight hits new areas of volatile material. This is not mere curiosity. It has real implications for tracking the comet's trajectory. Every jet emission, every flash can shift an object off its predicted course, raising the question for planetary defense planners about how well we can predict the trajectory of future interstellar visitors. European researchers have taken note of this.